do a lot of unique friction formulation testing. What this lab allows us to do is develop our own friction formulations in-house and then immediately test them on our Link chase machine or our Link brake dynamometers. So that greatly reduces the design cycle time from what used to be a couple weeks down to about 5 days. So one of the things we developed with this lab is our unique mu500 coating. What this coating does is it greatly reduces the bed-in time on the pads that it's applied to, and we found it was a unique application for StopTech Tactical. StopTech Tactical pads are uniquely designed and specifically formulated to work with high-intensity service vehicles like ambulances and police vehicles. For this particular pad, the user can put it on and be ready to go right out of the box. We also perform in-process quality control of our existing production samples. We'll pull samples out of our incoming shipments, perform tests on them to ensure that they meet the baseline requirements that we've defined. So after Dr. Lee has formulated a new friction sample for us, what we tend to do is put it on the dyno for full-scale testing. One of the first tests that we run with all of our friction is a noise test. That's the SAE-J 2521 industry standard noise matrix test. The reason we do noise is because it's the largest customer complaint. If the pad is noisy, the customer is unhappy with the product, so we want to ensure that all of our friction is silent when it arrives to the customer. After we run the noise test, we'll run a friction coefficient test, which is again the SAE-J 2522 test. That gives us an idea of the friction performance at different temperatures and pressures. Once we're done testing that, we'll move on to a wear and dusting characteristics test, which is the SAE-J 2707B. This test simulates some real-world driving scenarios and gives you an idea of how the pad and rotor are going to wear together in real-world driving environments. Now, once all three of those tests are done, it's a lot of data that we need to compile to understand how these friction formulations compare against one another. So what Dr. Lee did was develop this beautiful spider chart here. And the way this works is the best performance in each of these categories will be towards the outside of the spider chart. So as you can see here, in fade resistance, all three of these pads, pad A, B, and C, have similar fade resistance performance. However, when we get to pad life, you'll notice that the green formulation has better pad life than the blue and the red formulation. Again, with noise abatement, you can see here that the green and the blue are right on top of each other, indicating that those would be silent pads versus the red pad, which is going to make a little bit more noise. So once we have these spider charts, we're able to compare different friction formulations and understand how those compare to one another. We also do OEM baseline testing as well as competitive baseline testing. So when we do that, we can put those on the spider chart as well and understand how our friction compares to competitors and OE as well. Right now I'm standing in one of our full-scale Link brake dynamometers. This is an NVH cell, which means the interior is actually isolated from the outside noise. That allows us to run the industry standard SAE-J 2521 test. As you'll notice, there's a microphone here. This will actually pick up any noise events that occur between the brake pad and the rotor assembly here. This is just one of our dynos. We actually have two more and a third smaller scale dyno called a chase machine that we use to qualify our product that we formulate in the lab. We've got some thermocouples. One's attached to the rotor and one is attached to each pad. The rotor thermocouple actually serves as the control temperature for the test. So every stop is run from a prescribed temperature. In a lot of cases that's 100 C, for instance, 212 Fahrenheit. What that means is the brakes will not apply until that temperature is reached. So the dyno will spend its time cooling the rotor until it reaches that temperature, and then the brakes will be applied. That allows us to compare these tests against one another and know that they're all run from the same temperature. So as we talked about before, we're able to run all three of our important tests. That's the noise test, friction coefficient, and wear test. We're also able to run our own unique tests. Sometimes we'll take some data from a vehicle and run our own driving style simulation tests in here as well. So you'll notice we have two air ducts here. This is actually the supply air. So that's blown across the rotor, and what that's done is to simulate cooling air that you would see on your vehicle traveling at a specific speed. This vent here is for exhaust. Air is actually sucked outside the dyno, so it helps us collect some of the debris or any dust that's being generated and pulled out through our dust collector and then exhausted clean air into the atmosphere. So what you're seeing here is a brake corner group for a Ford Crown Victoria, a D931 pad shape. We're able to test pretty much any pad shape that's out there in the market. We create unique fixtures that help the rotor attach to the dyno, and then we have a unique fixture for the caliper. Once we design those, we're able to simulate the inertia of that particular vehicle. Back behind this wall here, there's a large inertia cabinet with rotating plates. We change those plates to simulate different inertias for different size vehicles. A smaller car will receive less inertia, and a larger car like an F-250 would receive more. These dynos are running 24/7, and we're constantly changing new materials and adding new products to these dynos to ensure that we're continuing testing.